Hi, everybody, and welcome to Lecture 2 in Environmental Sciences 347, Introductory to Climatology. I'm your instructor, Sean Sublett, and in this lecture, we'll be looking at the scale of the Earth system, the two ways to think of scale in the Earth system, one in time and one in space. We look at the means and the anomalies, which is basically the difference from the means or the long-term average. And we'll examine the tools that are used to examine the system, to measure the system, and to better understand how it operates. So that's how we'll get started with Chapter 2. We start with the driving question about scales. And really there are four fundamental spatial and temporal scales when we think about climate variability and ultimately climate change. The first one is the macro climate. That extends over larger areas up to continental in size. So as we think about Lynchburg in particular, we think about the Virginia Piedmont locations as a macroclimate, anywhere that's just immediately eastward from the Blue Ridge all the way to the fall line. Let's say that area between about Lynchburg and Richmond, or from Charlottesville to Fredericksburg. That's the area we would consider the Virginia Piedmont. Mesoscale climate, characterized with smaller, more physically distinct regions like metropolitan Lynchburg, the size of a larger metropolitan area, for example. That's a good idea of a mesoclimate. But then local climates take that one step further down. Let's say a neighborhood, a city, a field, a marsh, a forest. That's kind of a local climate. And then one spot further down is a microclimate, and that's a very tiny area, just a few square feet or square meters, an individual farm, a field, the slope of a hill, a marsh, an area near a creek, the top of a mountain, a ski slope. Those are all examples of a microclimate. You can see there the idea for the scales and dimensions, both horizontally and vertically. The macroclimates can be easily more than 12 miles in horizontal dimension, whereas the microclimates can be less than a meter or yard. So those are the four scales that we think about, from the micro all the way up to the macro. Thinking about climate variability and climate change, these are two key differences to take note of. Climate variability are essentially the variations within the system, the variations around a mean or an average state that we use statistics to calculate, whereas climate change is a systematic fluctuation in those long-term statistics in one direction or another. In other words, you could think of climate variability as some occasional ups and downs, but climate change takes those ups and downs, but there is a net up, or takes those and there is a net down. All right, so those are the two big changes, the two big explanations. Variability is that change within the system. Climate change is moving that system into an entirely different paradigm. So an anomaly, by definition, is the departure from a long-term average. And it doesn't necessarily occur with the same sign or magnitude in all locations. Positive anomalies are above long-term averages. Negative anomalies are below long-term averages. So oftentimes we hear the term positive and we think that's a good thing. Here we're talking about it in mathematical terms. So positive anomalies doesn't mean it's necessarily a good thing. It just means it's above the long-term average. And negative is the other way around. Doesn't mean it's necessarily bad, but it does mean it's below a longer-term average. So here's an example. I took this from a week or so ago. We're looking at the Pacific Ocean temperatures, both the observations and the anomalies. And this is along the equator in the Pacific Ocean. If you look closely at the bottom left there, you can see Australia, and the Americas are on the right side. And that top feature, you look at the scale of temperatures, and this is in Celsius, where the blues are cooler, 17, 18, 19 degrees Celsius, and the warmer colors are 28, 29, 30, those reds and oranges. So that's the observations. But then for that very same time, you look at the bottom graphic. It's the same time and the same domain, the same physical space. But we look at how those current readings are different than the long-term mean or the long-term average. And in this case, you see right in the center part of the screen and back down toward the bottom right or toward the southeast, it's a little bit cooler than normal or the long-term average. Whereas on the far left part of the screen in the upper left, it's warmer than the long-term average. And that can sometimes tell us a lot about what to be expected in terms of the sensible climate or the sensible weather in the short term. And we'll talk more about that in just a second. And oftentimes the conventions are this way. The blues tend to be negative anomalies. The oranges and reds tend to be positive anomalies. This is looking down from above the Earth on a different projection. And here the squiggly lines are what's technically called geopotential heights. But basically this is how the flow or the winds aloft up at around 18 to 20,000 feet are flowing across the northern hemisphere. And you can make out, if you look closely here, North America, and this big bulge to the north here along the west coast in Alaska, and then this big dip down to the south here in eastern North America from Hudson Bay all the way down to Florida. So this shows you that the winds are a lot farther north, or you have a positive anomaly. Here the winds are a lot farther to the south, or it's a negative anomaly. All right, so not surprisingly, in this type of a wind flow pattern, it's going to be a lot cooler in the eastern U.S. and North America, and a lot warmer than normal in the western U.S. and North America. So back to the previous example, again, looking at the Pacific Ocean, we're looking more at the anomalies in the bottom part of that image. Look at that broad area of below normals. This is coincident with what's called a La Nina, and we will talk about El Nino and the Southern Oscillation and La Nina a little bit later. But the short version is La Nina is a periodic cooling of the equator, the Pacific Ocean, along the equator. And there's also the converse of that, the El Nino, which is the periodic warming of the water in the Pacific Ocean along the equator. But we have to use these anomalies, these differences from the long-term average, to try to find these kinds of climate fluctuations and climate internal variabilities. We also see this here in the states regarding temperature. This is a product that was issued from the National Centers for Environmental Information. They do this every month. They compute what the statewide temperature rankings were. And at the end of the year, they sum it all up. So this is the statewide average temperature rankings for the entire year, 2020, and using the period from 1895 to 2020. So 1895 is the first real strong year of the instrumental record in the United States. And the rankings there are at the bottom. There are no blues on this map because 2020 was a very warm year. So all those states you see that are orange were much above average. There was no record warmest year last year, but every state in the union, or at least the continuous 48 states, was above normal in the year 2020. And in this particular example, the average is the 20th century average from 1901 to 2000. So for this particular example, the average temperature was taken for the entire 20th century. And then we looked at what the temperature was from 2020 and compared 2020 to the long-term average from 1901 to 2000. So that shows that Virginia there, 125, was the second warmest year on record. One by convention in this map is the coldest. 126 by convention is the warmest of the 126 years in the period of record. And this is also calculated for precipitation, the statewide precipitation ranks. And in 2020, there was a very big difference between the wet year in the southeast and the very dry year in the Intermountain West and in the Great Basin. In fact, that deeper brown you see with the ones in Nevada and Utah indicate that 2020 was the driest year on record in those two states. There's no state that had the wettest year on record, but 124 in Virginia, 125 in North Carolina. These are showing you that these were the second and third wettest years on record. And like the temperature plot before that, this is compared to the 20th century average. So for January to December, all of 2020, Virginia had its third wettest year on record. All right, and so it was much, much above average, with the average in this case being from 1901 to 2000. So when we look at the anomalies, when they start to build up a bit, when we start to see these anomalies pooling in one direction or another, these can give rise to feedback loops. All right, so if you have many different things going on in the climate system linked together and interacting, they can cause the climate to go in one direction and fly off in one direction, or they can kind of start to go in one direction and return it safely, if you will, back to the original state. All right, so there's a positive feedback and a negative feedback. You can think about that as an unstable equilibrium and a stable equilibrium. All right, so some examples here. To the left, that's an example of a negative feedback. And in this case, negative means it's returning to the main state. It's returning to the condition it was originally. That's why we associate that with stable. So a negative feedback is stable because it's returning it to the original state. All right, so for the example on the left, there's a rise in surface temperature. All right, so on the Earth, there's a rise in surface temperature. So as a result, there's going to be an increase in evaporation from the ocean surfaces. Okay, well, that's fine. Warmer air evaporates more. That makes sense. But then you end up having more low clouds. All right, well, that's fine. But now you have more clouds into the atmosphere. But the sun reflects off the top of the clouds. So you're starting to decrease the amount of heat energy coming into the Earth's system. So then that will drop the surface temperature. So that kind of returns the system back to where it started. All right, the negative feedback is a stable equilibrium, if you will. Flip side of that is the unstable equilibrium. If there's a rise in surface temperature and an increase in evaporation, but that also could mean a more humid atmosphere, meaning more water vapor is in the atmosphere. And like carbon dioxide, water vapor is a greenhouse gas, meaning that it effectively traps heat. That's a little bit of a misnomer, and we'll explain why later. But for this example, it enhances the greenhouse effect, which will then further take the temperature up. So that's a positive feedback example, or an unstable equilibrium. In other words, you kick the system in one direction, it goes flying off in that direction. As opposed to the first example, the stable equilibrium, where you kick it, but then it rolls back. You can think about a ball in a valley for the negative feedback example. If you have a ball in a valley and you push it up the hill, it rolls back and stops again. All right. The converse of that, the unstable equilibrium, you've got a ball on top of a mountain. All right. And it's just sitting there. As long as nothing messes with it, it just sits there. So it's in an equilibrium state. But as soon as you give it a little push, it goes rolling right down and nothing's going to stop it. So that's the example of a positive feedback or an unstable equilibrium. And these are two examples on the screen that actually will work to counteract each other a little bit. So that's why even though the temperature, our surface temperature is rising, how fast it rises depends on which one of these feedbacks is dominant over the other. And this leads to the idea of a tipping point in that unstable equilibrium. All right, it's a critical point or a threshold in which there's effectively no going back. Like there's a fundamental change in the system. Right now, the thought about what kind of a tipping point could we have with climate change is the Greenland ice sheet. At what point does the system warm up enough where the whole thing begins just to melt into the sea? All right, and that's not something that's going to happen in 20 years at all. That's something that would easily take 100 to 200 years at the absolute minimum. All right, but we could theoretically reach a point where we've warmed up the atmosphere enough where it just doesn't get cold enough in the summer or stay cold enough in the summer in Greenland to maintain ice like it does now, so that ice sheet ultimately melts down into the Atlantic Ocean. So how are some ways that we do these measurements? The first one is what's called an in situ measurement. In other words, you're physically measuring the thing with some type of an instrument that's within the realm or within the sphere that you're measuring. All right. For example, this contraption you see here is called the Automated Surface Observation System. This was largely installed, numerous ones of these were largely installed across the United States in the middle to late 90s. And they are measuring temperature because the air is kind of running through the sensors. They are measuring visibility. They are measuring wind speed and direction. The wind hits the sensor, so we know how fast it's going. There's an electronic thermometer that changes. The resistance changes with the temperature. So we're directly measuring some of these variables. Another way we do that to get information that's not necessarily on the ground but into the sky is with a radiosonde. It's a small instrument package with a radio transmitter that's launched by a weather balloon 2 times a day. And the image you see on the right there, the big balloon, the big sphere to the top, that's the balloon itself. You can see a little orange parachute below that, and the little guy there is holding the instrument package. He'll let that go, and that will typically go up to about 100,000 feet in the sky. Then it will pop, and the parachute will open up, and the radiosonde will slowly fall back to Earth. But there's a little instrument packet on there that is measuring the temperature and the humidity. And there's a pressure sensor on there. And there's a GPS so we can locate it. That helps us tell us what the wind direction and speed are doing much higher up into the atmosphere. So these are done in numerous locations throughout the world every 12 hours. Conversely, there's the drop wind sonde, which means unlike a ray wind sonde, it's not launched from a balloon. It's up in an aircraft for the most part and then just dropped. This isn't used very much with the exception of when there's maybe sure I get this right. The NOAA hurricane hunters fly into hurricanes to do reconnaissance missions, to gather data on the hurricanes, to get them back so we can make better forecasts. So when the NOAA hurricane hunters fly into these hurricanes, they'll drop these instrument packets through the hurricane to get measurements in the vertical of pressure, temperature, humidity, and wind. And that gives us an idea of what the structure of the storm is in the vertical. Oceans are a lot harder because you're not walking on the oceans. So you've got to have ships, buoys, floats, gliders, submersibles, autonomous instrumented platforms, all kinds of stuff to try to get data from the oceans. Lots of these are just buoys. There's a lot of buoys out there. All right, but even so, we can't have but a certain network of buoys that's going to give us the data we need to make better forecasts and to understand the system. One of the newer technologies that's come around in the past 15 or 20 years are called Argo floats, and they do float, but they are able to dive remotely to a certain depth into the ocean, take their readings, and then come back up. And there's hundreds of these, mostly the Pacific Ocean, because the Pacific is so vast. But these give us some kind of idea of a temperature and salinity profile in the ocean. And the warmest part of the ocean, as you might guess, is at the very top, and it gets much, much colder as you go down to the bottom of the ocean because you're not getting a lot of sunlight getting 2,000 meters down into the ocean. Now, we can't be everywhere all the time, so fortunately, we could do some remote sensing by a satellite. So, previously those were all in situ measurements of things that were actually in the medium that we're measuring. So this is remote sensing. We're not in the medium that we're sensing. We're looking at it remotely. And for the most part, these are sensors that are observing Earth from orbit, either low Earth orbit or geosynchronous Earth orbit. And we'll talk about the difference of those in just a minute. But basically, we're looking at different waves in the electromagnetic spectrum and then using that data or that information about the energy coming off in those wavelengths to then cross-reference what we know about the Earth system to make some sense of what we're seeing. All right, so a little bit of a background about the electromagnetic spectrum. The electromagnetic spectrum is basically involves all EM radiation. It's a form of energy as well as a means of energy transfer, and these go as waves. All right, and most of these waves are invisible. All right, longer wavelengths are things like radio waves. All right, shorter wavelengths are things like gamma rays. All right, it's these shorter wavelengths that have much, much higher energy, and those are the things that if you're exposed to those, start messing with your DNA, so it's not something you want to play around with. Fortunately, there's not a lot of that running around naturally. Long wave radio waves, the waves are so long, they're not messing with your body very much. That's why we can have very high energy radio transmitters. If you think about the classic FM radio waves, they travel a very long distance. They can travel through walls a lot easier because they're big, long waves. The length between the waves is very high. Then in between that, as those wavelengths get a little bit shorter, you get toward microwaves, then infrared radiation, and then visible light. Visible light is a very, very narrow part of the full electromagnetic spectrum. All right, and then once you get past the higher energy of visible light, which is blues and violet, you get ultraviolet radiation, and then X-rays, which, surprise, you use X-rays to see through you because they're higher energy particles, so they get through your skin and then bounce off your bones. And then the much higher things are gamma rays, which we're not messing around with. All right, but since your cell phones aren't using X-rays and gamma rays, you don't have to worry about those too much. So when we talk about the wavelength, that's the distance between the wave crests, and the frequency are the number of crests that pass through a specified period in time. So the satellites fly in two different kinds of orbits. One of them is called geostationary, and the other is a polar orbiter. Geostationary satellite in the left there goes around the Earth at the same rate that the Earth is spinning on its axis. So that's out 23,000 miles above the equator. So because the satellite is going around the Earth at the same rate that the Earth is rotating, it's over the same place all the time, so we can have constant coverage of a particular point on the Earth. That's how weather satellites, for the most part, work. When you look at satellite imagery, weather satellite imagery, you're normally seeing stuff from a geosynchronous satellite. The polar orbiters are in a much lower Earth orbit, only a few hundred miles above the Earth's surface. But because they are closer to the Earth, you get a much better coverage in space, spatial coverage, higher resolution of whatever you're trying to sense. You don't get to see the same place all the time because the satellite's going like this while the Earth is going around like this. So 2 times a day, you will see the same spot on the Earth as the satellite goes up and down as the Earth goes around. So polar orbiter, you get very good spatial coverage, but you don't get it consistently. Geostationary, you get consistent coverage, but it's just not as accurate or as high of a resolution. The sensors on the satellites come in two types. There are the passive sensors, which are just kind of taking in the energy that is being emitted by the Earth system. These are passive sensors, because the Earth is always giving off energy. Most of it is in the infrared, so you tweak your sensors to look in the infrared part of the spectrum. All right, but there are also active sensors, which will send energy down to the Earth and then wait for something to bounce back, kind of like a radar. So you send down some kind of energetic pulse and then wait to see what comes back. So passive is just up there sensing the natural, if you will, energy that's coming off the Earth. Active, like radar, is sending some kind of signal down toward the Earth and seeing what bounces back. So this is what we call a visible satellite image. This is in the visible part of the spectrum, and I took this image on Monday afternoon. And this is just the United States. You could see all the clouds in the eastern U.S. with the snowstorm we had here in the Northeast. While it was clear in Oklahoma and Texas, it was a sunny day there, and a new system moving on to the West Coast. Again, that's in the visible part of the electromagnetic spectrum. So that's passive. Here's the infrared image, and this is a lot. It's not as sharp because again we're sensing, we're just taking in infrared information from the Earth, but it's basically is doing colors. In other words, it's sensing temperatures. The brighter whites here are showing you what temperatures are. The grayer colors are showing you where it's warmer. So brighter whites are colder. The grays and darker colors are warmer. And most of the time, this corresponds pretty well to cloud heights. So when it's nighttime, this is probably the best game in town to figure out where your clouds are in the night. Now, some of the newer satellites that have been launched the last couple of years actually have a nighttime visible, which can sense some clouds in the visible part of the spectrum just from moonlight, which is pretty neat. But those aren't very reliable for forecasting purposes. So most of the satellites you see are from NASA or NOAA. Again, everybody's familiar with NASA, but NOAA is the National Oceanic and Atmospheric Administration. They're the ones that are kind of managing the weather satellites once they are in orbit. But there are also some use from the Environmental Protection Agency and the U.S. Geological Survey. So there's a number of instruments on these satellites, especially the low orbiting satellites, that can monitor high resolution parts of the climate system. For example, this is from NASA's Aqua satellite. This is one of these low Earth polar orbiters that's just able to resolve a dust storm over Iraq in 2009. This is not something you're going to see very well from a geosynchronous satellite that's out 23,000 miles from the surface. So to get the high resolution features, you need to have the lower Earth orbit or those polar orbiters. Now, thinking ahead a little bit about the system as a whole, since the United States is only one part of the Earth, there is some cooperation internationally with data gathering and science and data sharing. When we think about climate change, a lot of this is, I don't want to say regulated, but a lot of this is kind of congealed or come together or presented together by the IPCC, the Intergovernmental Panel on Climate Change. They were formed in 1988 by the WMO, the World Meteorological Organization, and the UNEP, the United Nations Environmental Program, UNEP. And this is all a division of the United Nations. All right. And their job is to evaluate the state of the climate science periodically. The IPCC isn't doing any original research. They're basically surveying the research that's being done and then reporting it back to decision makers, governments, heads of state, policymakers, and the like. The next one of these assessments is due later this year, 2021. It's called Assessment Report 6, or sometimes you'll just hear it as called AR6. And these are broken into 3 primary working groups. The first examines the true physical science. What does the hardcore data tell us about the Earth system and where it's going in a changing climate? The second group looks at the impacts of the changing climate, the adaptation strategies, and where the greatest vulnerabilities lie. And then mitigation, which is limiting or preventing greenhouse gas emissions and enhancing activities that remove them from the atmosphere. What are we going to do about this? What are we going to do about what's happening? Adapting is kind of getting ready for it. Mitigating is like, well, is there something we can do to prevent it or limit those impacts? And that comes out from the IPCC later on this year. A couple things to wrap up. We talk about models a lot. We hear a lot about weather models and climate models in the last 10 years or so. A model is a representation or a simulation of a system. It uses some of the essential features of a system while kind of omitting some of the details that aren't as important or hard to predict. But sometimes things that are hard to predict are essential, and that's when you have to make guesses. Sometimes those are called parameterizations. So a model is an approximate representation. It's not perfect, but it's the best guess. And there are different kinds of models. There's a conceptual model, a statement of a law or relationship, organizes the data, describes interactions between systems. These are things like fronts. You've heard of a cold front or a ward front. That's a conceptual model. All right, we've got cold air advancing from the Arctic into a place that isn't quite so cold. As that cold air advances, hits that warm air, it rises. This is a conceptual model of what's going on in the atmosphere. A graphical model is kind of what the name implies. It kind of illustrates and displays the data in a format that conveys more meaning, or sometimes we hear about data viz. And that's what a graphical model is all about. A physical model is a small scale portrayal of the system, whereas the numerical model is something it's kind of like the physical model, but it's all in mathematical representations. In other words, there are certain properties, physical properties, chemical properties that we understand and we can represent very well mathematically. All right, whether that's temperature, that is pressure, that is humidity. There are certain equations or relationships that we understand about the atmosphere that we can then put into a numerical model. We can solve certain equations, very fundamental equations about relationships between pressure and humidity and temperature. All right, and that can give us a big numerical weather model. This is the foundation of all forecasting that you see today. And this is done at the Numerical Weather and Climate Forecasting Center in Washington, D.C., the National Centers for Environmental Prediction. They were the only ones doing this until about 15 or 20 years ago. But in that time, there have been a number of private organizations that have started to develop their own numerical forecasting models. And not every model works the same. Some models work better than others at different time scales because there are certain relationships that are very well known to work on short time scales and certain mathematical and physical relationships that are known to work on much longer time scales. All right. So when we think about on the vertical axis there, the things that are forecast in time and space, there are very short-term things like a weather warning, like a severe thunderstorm warning, a tornado warning. That's just a few minutes from now. There are things like severe thunderstorm watches, which forecast for a few hours from now. Or just the regular, this is what it's going to be like today forecast. Then we look at things that are more like outlooks, where we don't understand the specifics, but we have a broader understanding of how things are going to pan out in the next, let's say, 1 or 2 weeks. Like we know about a week from now, it's going to get very, very cold in the eastern United States. And then you look at much broader outlooks, seasonal, yearly forecast. These are much, much harder. And there's almost nothing you could say about the day-to-day weather 40 or 50 years in advance. That's just something you can kind of try to manage from a statistical analysis. So the short-term forecasting is the backbone of this is from INSEP's Climate Prediction Center and Weather Prediction Centers. But when we think about the climate scale forecasting, these are 30 and 90-day outlooks that are issued very frequently, a couple times a month for the United States and its outlying areas. This one I pulled down just today is the temperature outlook to the top right for February and the precipitation outlook for February of 2021. So this suggests that most of the country is going to be cooler than normal and wetter than normal. All right, and again, looking at the longer term average here. Florida on the top right there, probably going to be warmer than normal, but also drier than normal. We look at the Great Lakes, they look like they're going to be cooler than normal and wetter than normal, which oftentimes means snow this time of year. So they don't give specifics about a certain day, but they give you a general idea of when we think about what the average is. These are the forecast anomalies, going to back what we said before. These are how we expect the internal variations of the climate to react in this 4-week period that is February 2021. Thinking even longer term, we talk about global climate models. These are numerical models that are different than weather models. The weather models are taking the current state of the system and seeing how it reacts. The global climate models are changing the outside conditions, or what's called the boundary conditions of the system. All right, so a weather model is looking how the system is changing internally. These global climate models are saying how is the system going to be perturbed when we act on it externally. And by externally, in this case, we mean we're adding greenhouse gases. All right, so this is one example of that projected annual average temperature change in the last 20 years of this century. Again, so we're not saying this is the temperature on July 14th, 2085. No, this is like for two different scenarios. One on the left there is for a lower emission scenario. In other words, there is fewer greenhouse gases compared to higher greenhouse gases on the right. All right, so this suggests that, oh, surprise, there's going to be a lot more warming in the overall system, the Earth system, if you put more greenhouse gases in the atmosphere than you don't. So you can think of these as kind of a sim Earth, if you will. What are you doing to the outside of the system to force it in a certain direction, compared to a weather model where you're just looking at how those internal actions are going to change. Think of this as another analogy, the difference between how you would build a car and what you would do to keep that car running. So how the car runs is weather. How you built the car is more along the lines of climate. So that's the lecture for today. Again, reviewing to understand the scales of weather and climate, the differences between anomalies and the means, and some of the basic tools to understand the system. So thanks for attending the lecture. Next one we'll do, lecture 3, is going to be about energy in the Earth system, energy in and energy out, and how that drives the climate system.